Good morning all. Welcome to my video class. വേവ് ഒപ്റ്റിക്സ് എന്ന ചാപ്റ്ററുമായി ബന്ധപ്പെട്ടുകൊണ്ട് നമ്മൾ ചെയ്ത 4 വീഡിയോ ക്ലാസ് നിങ്ങൾ എല്ലാവരും കണ്ടിരിക്കുമെന്ന വിശ്വാസത്തോട് കൂടിയിട്ടാണ് നമ്മൾ ഇന്ന് 5ാമത്തെ ക്ലാസ്സിലേക്ക് പോകുന്നത്. കഴിഞ്ഞ 4 ക്ലാസ്സുകളിലായി വേവ് ഒപ്റ്റിക്സ് എന്ന ചാപ്റ്ററുമായി ബന്ധപ്പെട്ടുകൊണ്ടുള്ള തിയററ്റിക്കൽ പോർഷൻ നമ്മൾ ഓൾമോസ്റ്റ് വളരെ ക്ലിയർ ആയി നമ്മൾ ഡിസ്കസ് ചെയ്യുകയുണ്ടായി. 2D 3D ആനിമേഷൻസിന്റെ സഹായത്തോടുകൂടി വളരെ ഡീറ്റെയിൽ ആയ കാര്യങ്ങൾ നമ്മൾ ചർച്ച ചെയ്യുകയും ചെയ്തു. നിങ്ങളെല്ലാവരും ഈ 4 ക്ലാസ് കണ്ടിട്ടുണ്ടാകും എന്നുള്ള വിശ്വാസത്തോടു കൂടിയിട്ടാണ് ഇന്നത്തെ 5ാമത്തെ ക്ലാസ്സിലേക്ക് വരുന്നത്. ഇന്നത്തെ ക്ലാസ്സിൽ നമ്മൾ ചെയ്യുന്നത് വേവ് ഒപ്റ്റിക്സ് എന്ന ചാപ്റ്ററുമായി ബന്ധപ്പെട്ടുകൊണ്ടുള്ള ന്യൂമറിക്കൽ പ്രോബ്ലം സോൾവ് ചെയ്യുകയാണ് ചെയ്യുന്നത്. സോ ഈ ക്ലാസ്സിലേക്ക് വരുന്നതിന് മുൻപ് ഈ ക്ലാസ് പർപ്പസ്ഫുൾ ആവണം എന്നുണ്ടെങ്കിൽ തീർച്ചയായും നിങ്ങൾ കഴിഞ്ഞ 4 വീഡിയോ ക്ലാസ് നിങ്ങൾ കണ്ട് ആ കാര്യങ്ങൾ നിങ്ങൾ മനസ്സിലാക്കിയെങ്കിൽ മാത്രമേ നമുക്ക് മുന്നോട്ടേക്ക് പോകാൻ സാധിക്കുകയുള്ളൂ. സോ ക്ലാസ് കാണാത്ത ആളുകൾ തീർച്ചയായിട്ടും ഈ ക്ലാസ് കാണുന്നതിന് മുൻപായി കഴിഞ്ഞ 4 വീഡിയോ ക്ലാസ്സുകൾ നിങ്ങൾ കാണണമെന്ന റിക്വസ്റ്റോട് കൂടി നമുക്ക് തുടങ്ങാം. Once again, I welcome all of you to my video class. So let's start with the first question. The first question is displayed on the screen. So you have to pause the video and write the question into your notebook, and after that we have to start the question. For my convenience, here I am reading the question once again. So the first question is, a monochromatic light of wavelength 600 nanometer, that is, it is given the wavelength lambda is equal to 600 nanometer. So it is given in our question, is incident from air on a glass surface. So once again I am reading the question, a monochromatic light of wavelength 600 nanometer is incident from air on a glass surface. So in our question it is given lambda is equal to 600 nanometer. And also, what are the, so here you are asked to find what are the wavelength and frequency and speed of the refracted light. So in our question it is saying you are asked to find the wavelength, frequency and speed of the refracted light. And also it is given the refractive index of the glass is 1.5. So these are the data given in our question. So by using these data, you need to find the wavelength, speed and the frequency of the refracted light. Now, to find the wavelength of the refracted light, it is given lambda is equal to, that is wavelength in the first medium, that is wavelength in the air, it is given that 600 nanometer, and the refractive index of the glass is 1.5. We have the relation in between the velocity, frequency and the wavelength, that is V is equal to F lambda. This is one of the fundamental equation related to the electromagnetic waves. So here V is the velocity of the wave and F is the frequency and lambda is the wavelength. If so, we have to write in the first medium, that is in air, we have to write V1 is equal to F1 lambda 1, and in the second medium, that is in glass, it is V2 is equal to F2 lambda 2. As we know, when the light travels from one medium to the another medium, there is no change for the frequency of the light. That means we have to write the frequency of light in the air is equal to frequency of the light in the glass. That is, F1 is the frequency of the light in the air and F2 is the frequency of the light in the glass. So we have to write F1 is equal to F2. If so, from this equation we have to F1 and F2 are same, so we have to write V2 by, so we are rearranging the equation, so we have to write it as V2 by V1 is equal to lambda 2 by lambda 1. So as you know, from the definition of absolute refractive index, we have N21 is equal to V1 by V2, which is equal to N2 by N1. Here I am not coming to this equation because this is, we are already discussed in our previous classes. So here we are connecting these two equations. So when we are connecting the two, we will get V1 by V2 is equal to N2 by N1 is equal to lambda 1 by lambda 2. Here you don't need to any confusion because here V2 by V1 is given. So in our problem we are writing it as V1 by V2. So we are taking the reciprocal. So V1 by V2 is equal to N2 by N1, that is equal to lambda 1 by lambda 2. That is, we have V1 by V2 is equal to lambda 1 by lambda, that is equal to N2 by N1. So from this we have to write N1 lambda 1 is equal to N2 lambda 2, just cross multiplying the above. So from here we need to find the wavelength of the refracted light. That is, we need to find the value of lambda 2. So we have to write lambda 2 is equal to n1 lambda 1 divided by n2. Simply we are substituting the values of n1 lambda 1 and n2. Here n1 is the refractive index of the first medium, that is refractive index of the air, it is 1, and the lambda 1 is given in our question, it is 600 nanometer, that is 600 into 10 raised to minus 9 meter, and n2 is the refractive index of the second medium while doing its value is 1.5. So when we are doing the numerical mathematical tabulation, we will get the wavelength in the second medium. The wavelength of the refracted light is 400 nanometer. Now, to find the frequency of the refracted light, we are starting with the fundamental equation which connect the velocity, frequency and the wavelength of the electromagnetic wave. It is V is equal to F lambda. Here V is the velocity and F is the frequency, and lambda is the wavelength of the electromagnetic wave. So from this we have to write the frequency F is equal to V by lambda. That means to find the frequency of the refracted light wave, at the beginning I told when the refraction occurs, there is no change for the frequency of the electromagnetic wave. At the beginning there I told there is no change for the frequency of the light when it travels from one medium to the another medium. That means in the beginning I told F1 is equal to F2. F1 is equal to F2. So we are calculating here F1. F1 is the frequency of the incident light. So here the light is traveling through the air. So we have to write the speed of the light. V is the speed of the light. So speed of the light in the air, it is c by lambda 1. Lambda 1 is the wavelength of the light wave. In the first, we know the values of c and lambda 1. Simply we are substituting the value of c. It is 3 into 10 raised to 8 meter per second divided by lambda 1 is the wavelength of the incident light. It is given that 600 nanometer, that 600 into 10 raised to minus 9 meter. So while doing the numerical tabulation, there you will get the value of the frequency is 5 into 10 raised to 14 hertz. So this is the frequency of the light, frequency of the incident light. So at the beginning there I told the frequency of, there is no change for the frequency of the incident and refracted light wave. So we have to write it as F1 is equal to F2 is equal to 5 into 10 raised to 14 hertz. Now to find the speed of the refracted light, we have V2 is equal to F2 into lambda 2. So as you know, F2 is equal to 5 into 10 raised to 14 into lambda 2 is equal to 400 into 10 raised to minus 9 meter. So while doing the calculation, you will get, while doing the tabulation, you will get the velocity of the refracted light is 2 into 10 raised to 8 meter per second. So here we got the values of velocity, frequency and the wavelength. Now let's start the second question. So the second question is coming from the part interference. So before starting the problem, let's write the question. The question is displayed on the screen. In our question, it is given wavelength of the light lambda is equal to 5100 Armstrong. That can be written as 5100 into 10 raised to minus 10 meter. Now the width of the 10 fringes, that can be written as x, it is equal to 2 centimeter. And as from the definition of fringe width, we know fringe width beta is equal to x by n. Here x is the width of the n number of fringes and here n is the number of fringes. That we will get it is 0.02 meter. Here we want to find the value of slit separation d. So how can we find the slit separation d? We know beta is equal to lambda d by d. That means from that equation we have to write d is equal to lambda d by beta. Here lambda is the wavelength, d is the distance in between slit and the screen, and beta is the fringe width. So all these data, we know the values of all these data. So by substituting the values of lambda, d and beta, we will get the slit separation d is equal to 5.1 into 10 raised to minus 4 meter. That is the answer for this question. I hope that all of you got the idea how we got the slit separation. Now let's move to the third question. The question is displayed on the screen. And let's try the problem by yourself. If you find any difficulties, just go through the video, or else you have to do the problem by yourself. Okay. So the third question is from Young's double slit experiment. So here I am reading the question. In a Young's double slit experiment, the slits are 1 millimeter apart. That is, small letter d is equal to 1 millimeter. And the screen is kept at a distance of 1.5 meter from the slit. That is, the value of capital D is equal to 1.5 meter. 1.5 meter. So it is found that is the further statement is the one of the most important thing about this problem. So it is given that it is found that the fifth bright fringe is at a distance of 3 millimeter from the second dark fringe. Find the wavelength of the light used. That is the question that so you have to find the value of the wavelength of the light used. So for that it is given the distance in between the fifth bright fringe and the second dark fringe is 3 millimeter. Here I am picturizing that statement. So let's see how it comes. Here I am drawn the graphical representation of the interference pattern. So this is the central maxima. This is the first bright fringe, second bright fringe, third, fourth and fifth bright fringe, and again this is the first dark fringe, second, third and fourth dark fringes are shown in the figure. You know, the distance to the first bright fringe from the central maxima is beta. Similarly, the distance to the second bright fringe from the central maxima is 2 beta, and the distance to the third bright fringe from the central maxima is 3 beta, and so on to the fifth bright fringe. The distance to the fifth bright fringe is 5 beta. So it is given as 5 beta. Distance to the fifth bright fringe is 5 beta. Logically, we have to write the distance to the second dark fringe is 1.5 beta because it is coming in between first bright fringe and the second bright fringe. So logically we are writing the distance to the second bright fringe is 1.5 beta. If so, we have to write the distance between the fifth bright fringe and the second dark fringe is 5 beta minus 1.5 beta. So this is that is 3.5 beta. It is given as 3 into 10 raised to minus 3 meter. So the value, so this value is given in our question. So it is 3.5 beta is equal to 3 into 10 raised to minus 3 meter. So from this we will get beta is equal to 0.857 into 10 raised to minus 3 meter. And from the definition of fringe width, we have beta is equal to lambda d by d. Here capital D is the distance in between the slits and the screen, and small d is the slit separation in between the slits. So from this we have to write lambda. So here you are asked to find the wavelength of the light used. So here lambda is equal to, from this we have to write the lambda is equal to beta d by d. That while substituting the values of beta, d and d, we will get the wavelength lambda is equal to 0.531 into 10 raised to minus 6 meter. If you find any difficulty, you have to rewind the video or you have to contact me through the WhatsApp. I will give the further explanation for the problem if you find any difficulties. Okay, thank you. Now, let's move to the fourth question. So, as usual, the question is displayed on the screen. You have to write the question, and if you can, you have to solve the problem. If you are not able to do the problem, let's watch the video. There you will get the solution for that problem. So, here I am reading the question. In a Young's double slit experiment, the wavelength of the light used, that is lambda, is equal to 5461 angstrom. So here the question is, how many fringes can be seen in a width of 1 centimeter if the screen is at a distance of 1 meter from the source, that is the capital D is equal to 1 meter, and again it is given the slit separation is 1 millimeter, that is small letter d is equal to 1 millimeter. So in this question you are asked to find the number of fringes formed at a distance of 1 centimeter. That is, here the total fringe width is equal to, that is, here it is given the total fringe width x is equal to 1 centimeter, that is 10 raised to minus 2 meter. So from the definition of fringe width, we know beta is equal to x by n. Here x is the total width of the n fringes and n is the number of fringes. So from this we have to write n is equal to x by beta. The value of x is given in our question, but beta is not given. So from the definition of beta, we know beta, the fringe width beta is equal to lambda d by d. So simply we are substituting the values of lambda d and d. So we will get lambda is equal to 5461 into 10 raised to minus 10 into the slit the distance between the screen and the slit is d is equal to 1 meter divided by the slit separation d is equal to 1 millimeter, that is 10 raised to minus 3 meter. So while solving this, you will get the value of beta, and simply we are substituting the value of beta in this equation 1. Simply substituting the values of beta into the equation 1, that is n is equal to x by beta, that will give you the number of fringes formed. I hope that you can do the numerical side and just do the problem and find the answer for this question. So here I am stopping the fourth question. Till now we have discussed the problem regarding the interference patterns. Now we are moving to this next topic, that is diffraction pattern, and we will do that problem in our next video. Now, till then, keep safe, stay at home.